Hello, I'm going to present the TaRDIS messaging app demo. This is the outline of my presentation. I'll start by providing a brief motivation for this demo. Then I will explain how we use the different innovations in the TaRDIS toolbox to build the TaRDIS messaging app. I'll explain the relationship of this application and demo with the main TaRDIS use cases, and then we'll go on to the demonstration. So the goal of building this application was to provide a concrete example of a swarm and how this swarm could benefit from the innovations and tools in the TaRDIS toolbox. So by a swarm, I mean a distributed system that is composed by many different heterogeneous nodes that cooperate in a highly autonomous way to achieve a common goal. By heterogeneous, I mean that these devices might be different, not only because they have different amounts of computational resources, but because might have different architectures, capabilities, or even have different roles within the swarm to contribute to the overall goal of the swarm. Even the application logic executing within each device might be different. In this use case, this is true. We'll have devices participating in the swarm that are laptops like Macintosh or mobile devices like Android and Raspberry Pis. And the software they are executing, while being similar, has some differences. And by highly autonomous, I mean that there is no centralized control component or human intervention for keeping this swarm operating. It is effectively autonomous. More than that, it should be able to evolve and adapt to different conditions. For instance, some nodes failing or an increase in the total number of nodes in the swarm. So this application was built using innovation tools produced by TaRDIS and in particular by WP6. However, this application already paves the way for integration with innovations from other work packages. For instance, we could use the DCR graph choreographies built on WP3 to model and specify the applications that are running on top of this swarm. Or we can use the tools from WP4 to formally verify the decentralized protocols that are supporting the operation of the swarm. Moreover, we can take advantage of the data being produced by this swarm to inform WP6 so that they can train machine learning models that can support its runtime adaptation when it grows to a large number of nodes where it's impossible to track it by hand. So the application itself is quite simple. It's a broadcast application where different nodes in the swarm can broadcast messages to everyone in the swarm. These messages might contain attached files. So in our demonstration, we are going to use an access point, a wireless access point, to where every node is connected. This access point is not connected to the internet, so nodes are actually actively cooperating between them without access to resources in the cloud, for instance. So this simplifies the demo, but I should note that the software you're using could easily be used at a global scale, although we would need public IP addresses or modify slightly that software to deal with NAT. So this is a more convenient way to show the use case. In this use case, we'll have Raspberry Pis, and these are old Raspberry Pis. They are a 3B model that have 1 gigabyte of RAM. They are going to execute this TaRDIS messaging application and will generate periodically messages so that there is some activity in the swarm without human intervention. And then we'll have user devices. These might be Android phones or tablets or laptops. I'm using a Mac, but it could be Windows or Linux or something. So the application is quite simple. At the lowest level, every node in this swarm will join a logical network, also called overlay, where they'll have a few random selected neighbors, at most 5. Then we'll use this logical network or overlay to propagate messages using gossip. This means that when a device wants to broadcast a message, for instance, that laptop at the top left, he will just pick some of his neighbors at random and forward the message to them. When they receive the message for the first time, they'll do the same. They'll pick some random neighbors and send the message to them. Evidently, this can lead to some nodes receiving duplicate messages, but this is being handled by the gossip protocol itself that will detect these duplicates and eliminate them. The process continues until everyone in the swarm gets the message. Evidently, since the swarm is dynamic and the network is not reliable, it might happen that while a message is being propagated, a device is temporarily disconnected from the network. In this case, it would not receive the message. But in our application, we use an anti-entropy protocol that allows periodically every node to ask some random neighbor what messages do they have, and if it is detected that a message is missing, then the message can be sent to that node and effectively everyone gets a message. Let me start by explaining how we use different elements of the TaRDIS toolbox to build this application. Independently if the application is running on Raspberry Pis, laptops, or Android devices, there are also all applications written in Java taking advantage of either Babel Swarm or Babel Android frameworks. These are evolutions of the Babel framework that were produced in TaRDIS with support for self-configuration, self-management, and security mechanisms. In the case of the Babel Android variant, it also supports Android devices. At the lowest level, all nodes will join a logical overlay network that is managed by Hyper-V. Actually, this is a different version of the Hyper-V protocol that takes advantage of the self-configuration provided by Babel Swarm and Babel Android. When a node comes online, it will use multicast to find someone else that can introduce him to the overlay, allowing him to join the system. We also have a neighbor push gossip broadcast, which is a simple broadcast protocol that takes advantage of the neighbor information maintained by the local instance of Hyper-V to implement a gossip mechanism. We also have an anti-entropy protocol that uses the same information about neighbors to recover messages that might have been lost by a node. And we also implemented random tour. Random tour is a distributed protocol that allows nodes to estimate, using periodic messages, the size of the system. In the case of Raspberry Pis, there is an automated application that is using all of these protocols to generate messages periodically. Actually, each Raspberry Pi propagates a message every 30 seconds with a 10% chance. These messages contain some random attachment, and it also provides some information gathered from the automated app from the different protocols running in that device. For instance, the network size estimation. On the case of the laptop and the Android devices, there is a component called a messaging app control that acts more or less like a library and that exposes the functionality of the different protocols to a graphical component, which is different between the Android devices or the laptop. This messaging app control can, for instance, provide asynchronous information to the graphical interface, such as the messages that were received or information about changes in the neighborhood of a node. So before moving to the demonstration, let me speak a bit about the relevance of this architecture to the main TARDIS use cases. So you should note that broadcast is a fundamental coordination primitive in any decentralized and autonomous system like a swarm. Also, self-configuration is very important if we want to allow the system to evolve and adapt to new situations. So for instance, in the case of Telefonica, we can take advantage of solutions like the overlay management and the gossip broadcast that we're using to build federated machine learning systems that are fully decentralized and where different nodes compute locally and update locally their model and then use broadcast to share it so that everyone can act as an aggregator in the system. In the case of GMV, we can use anti-entropy to allow nodes to exchange information when they have the ability to do so due to the different orientation and position of antennas between satellites, so that they can exchange information about the navigational information that they know about themselves and other satellites. For the case of EDP, new R&D, they want to build a renewable energy market, and this will require devices that are part of the system to cooperate to match offers and demands from different consumers. This can be achieved using such an overlay like Hyper-V and some gossip protocol. And finally, in the case of Actix, they rely on an eventual total order broadcast primitive. We actually can build such a primitive by taking advantage of an overlay, a broadcast protocol, and some anti-entropy mechanism. And so we can extend the operation of the Actix by combining these protocols and even improving it for different scenarios. So moving on to the demonstration, there are two options basically. So if you have a laptop that has Java 21 or above installed, you can just go to the URL that I'm showing, download the app, and join the system. You must actually be connected to the wireless access point that we are using in this demo. Or if you are doing this on your own, just make sure that all nodes are connected to the same local network. Alternatively, if you want to experiment with the Android implementation, you can go to the link in this slide or just point your device to the QR code here and do the same thing. Launch your application, and then on both cases, you just have to pick some username and press connect. So before we move to that, let me show you a bit what you can expect from each of the interfaces. So in the case of the laptop application, you'll see an interface like this, which is, well, simple. And here on this drop-down menu, you can pick up the wireless network in which you are going to be connected and contacting other nodes in the swarm. In our case, it should be something that starts with that has an IP address starting with 192.168.0 something. Then you have to pick up some nickname in that box and then press start. When you press start, this TaRDIS symbol will light up. And this means that the application is now trying to join or has joined the swarm. You can double click that to get additional information about what is going on in the system, including information about the current neighbors of this application. You can also use the boxes and buttons to the right to write some message or maybe attach a file and send a message that will be distributed throughout the swarm. On the Android case, it's a very similar interface. So the dashboard in which the application starts, you have to provide some username and also use the drop-down menu to select the correct network to join the swarm, and then you can press connect. This will again light up the TaRDIS icon there. In the second tab, Messages, you can see the messages that have been received, and you can double-click those messages to see additional details. You can use the plus button to send your own message and maybe attach some file or photo. And finally, on the Notifications tab, you can see notifications of what's going on with the system, in particular, changes in the membership of the local node. And periodically, it also shows the current membership of that node. So let's now move to the demo. So what you see here is our Java application for laptops. Before starting the application in my laptop, I already set up in this room a set of devices. In particular, we have 4 Raspberry Pis and we have 5 mobile devices, all of them running the TaRDIS Simple Messaging app. And I also have an Android tablet next to me that is not yet running the application that I will use in the next segment of the demo. So now that we have the Java application, we can start by selecting the right network here and pick up some username, which I'll use Mark, and then start. So the system is now starting. It will look up for members of the overlay in the network and it will join. So as you can see, the icon here has light up, which shows that the application is running. We can actually press this button to see the numbers in this node. So as you can see here, we have 4 neighbors which have different IP addresses. Actually, the devices with 200 with IPs terminating in 200 are Raspberry Pis, and the others are the mobile devices. Meanwhile, we are receiving lots of messages from the different devices. And this happens because the devices, in particular the Raspberry Pis, are generating, as I told you before, random messages. We can take a look at one of these messages and see what's going on there. So as you can see here, we have a message sent by Raspberry number 4 that reports his memory usage, available CPUs, and its local estimation. He believes that currently the swarm has 13 nodes, which is a bit of an overestimation, but not by much. It also has a file with an attachment that we can open by pressing the Open button. That, as you can see, shows a window with the Java browser, the integrated Java browser, with the contents of the file. Raspberries are generating 64K bytes files with random letters. Okay, let's go back to the application and let's see what's going on with the Android tablet. So here I have my tablet, which is not yet connected to the system, but I will connect it now. So I'm calling it tablet and I can connect it. So here it is, it's connected. So now if I go to the notifications, I can see what's going on there. So as you can see, when I connected, I got several different neighbors, and then I disconnected from one unveil. This is because I want to have only 5 neighbors, and I already had 6. So I'm starting to receive messages from different nodes, which I can check if I click the message. Here it is. I can also save the attachment if I want. So as you can see, all of these things are integrated. And if we wait for a while, the Android, as you can see now, is receiving lots of messages. This is the anti-entropy working. Okay, so let's try to send a file and see what happens. So let's go back to the Java application, and now let's write a message. Here is a nice photo. And let's attach a file here. I'm attaching an image that I have in my laptop, which has, well, 2 megabytes. I'll send that message. And now let's go back to our tablet. And you'll see that we'll get the message. Here it is from Mac. So let's press it. So now we can see what is the attachment here. I can say that I want to view as a photo. And here it is. It's actually a photo of my cat. And if you look in the corner of the laptop, there is some code there, and that code belongs to TaRDIS also. So this was our demo of the TaRDIS Simple Messaging app. I hope you enjoyed it. Bye bye.